All right. This section is going to be a little bit different than the last ones. We're going to try and accomplish several goals at once. First off, this section is based on a book. It's a skinny book, so that's good news, right? It's a ebook that is included with the software. So if you want to, if you've downloaded the software already, you can go to the support ribbon under books and see the process improvement principles book. And basically that book is written as an easy read. Hopefully there's no executives on, so I can say the words. It's written as an executive understandable version of the book. So it was designed to that you could sit through and read each of the principles and understand them fairly quickly. It was not intended to teach anybody simulation, but it was intended to teach you some of the benefits of how I can improve the process and how I can use simulation to help evaluate those. So that's the purpose of the book. And there are also solutions to this are also in the examples folder in a subfolder of the examples. So you can go here and find that if you want, either now or anytime in the future. You can grab that. And if you really like paying for a printed copy of the book, you can go onto Amazon, and I think you can buy the book for $25 or something like that. So. Okay, so I said this is going to be a little bit different. So PIP stands for Process Improvement Principles. And together we're going to study a few of the PIPs to learn about the principles involved. While doing that, we're going to practice some of the simio concepts that we already know and learn a few more features and concepts that we've lightly touched on. We'll touch on them again lightly, but at least repetition breeds familiarity, hopefully. I'm only going to cover a few of the PIPs, but there are more in the slides. So in the unlikely chance that I get through this fairly quickly, we can go through more slides, or more likely when you download the slides later on, you can maybe use the slides as an example of what you might want to go through for additional study on your own. Okay, so to start with, I'd like to go through principle 1. So the principle is that variation degrades performance. And again, keep in mind, these are 25 principles that we try to illustrate. We identify the principle and then kind of prove that some aspect of it is true, and talk about what you can do to implement what you've learned there. So in this one, we're talking about variation degrades performance. And if you think back to our module 2 example of the car detailing, again, you can see an example there of how the performance got degraded dramatically. And in fact, we're going to do something similar here, and we're going to do a little bit of work with the interactive run with the simio interface and a little bit with experimentation. Actually, I'll probably go through this a little bit quicker, only because we already did cover something very similar to that. Okay, so to do this, if we connect, place a source server sync and connect with the 2 paths, set our arrival time to 60 minutes, our processing time to 55 minutes. That will basically reproduce our car detailing problem that we had before. So let's do this really quickly, since I think that's something that we can do together really quickly. So again, I'm going to do a file new. So we're going to place a source, a server, and a sync. And actually, I said paths in there, but let's just go directly to connectors. So we'll connect them up with connectors. And by the way, if you got ahead of me and did paths in there, remember you can right click on something and convert to something else. Okay, so we want to go into our source and set our source inner arrival time to exactly 60 minutes. So I'm going to put a 60, just type 60 in here and leave the defaults at minutes. So there's my inner arrival time coming 60 minutes apart. My process time, I want to set to exactly 55 minutes. So again, I wanted to illustrate that you don't have to have distributions everywhere. It is fine to put deterministic numbers where you know what the deterministic numbers ought to be. And then we'll come up here and set our, on the run ribbon, we'll set our speed factor to be 100, which will make it very fast. I'm going to zoom out a little. Well, no, I won't. I'll just leave it that way. And then run it and see what happens. So, not real interesting because there is no contention. Remember, our entities are coming in 60 minutes apart. They process for 55 minutes, and then it leaves. So there's never anything waiting, never multiple entities in the system at the same time. It's just very straightforward. Okay, so that's the simple case of this. Let's do a new experiment. Actually, let's, I'm going to shortcut this a little bit. Let's create reference properties for our inner arrival time and processing time. So we'll go back in here and our inner arrival time, instead of an inner arrival time of 60, we want to make this inner arrival time. We're going to right click on the inner arrival time. So on the word inner arrival time, we want to right click on that, set reference property, and then way down at the bottom, create new reference property. And we can just call this, well, let's just call it inter arrival time. And then on server one, we want to do kind of the same thing, processing time. We want to right click on processing time, set reference, create new reference property, and we'll just call this processing time. And anybody remember where we find the values that are used in here? We can either right click on the model and say show properties, or the shortcut is if we just click in the background, it shows the properties of the model. So there's my inner arrival time of 60, my processing time of 55. So if I want to change it to anything else, I could change it right here. But let's do an experiment. So let's do go into the experiment. So right click on the model and say new experiment. And so there's my two controls, my processing time, and what would we want as a to see the results of this? Let's see, what were we trying to prove here? We were trying to look at general performance. So general performance might be throughput, I guess, is as good a general performance as any. So let's add a response. So again, I'm in the experiment, and up here I want to add a response. And for my response, I want this response to be throughput. And in throughput, where would I get throughput from? Well, there's a couple different ways, and I showed you before how to get it from the sink. But there's another way to get it. So just to help confuse you a little bit more, I'll go to someplace else and get it. The default entity has a population, and that population has a number created, number destroyed, number in system, time in system. So there's lots of different ways we could get at this. But if I did time in system, number observations. So that basically is a odd way of going out and saying, remember how many entities have left the system? Because we only record time in system when they leave the system. So I'm going to get time in system as my throughput measure. So that is number of entities, so I don't need to specify a time on it. Okay, so now if I just run that, I had 24 entities come through the system. Well, that kind of makes sense because they're coming in 60 minutes apart. And I ran it for 24 hours. So let's set up a couple other controls. So if we set up another control and just set it to be a random exponential inner arrival time. So if you remember how to spell that, and random exponential with an average of 60 inner arrival time. Oh, what did I do?
I think you're missing an R in random.
Yep, I typed it, really. Okay, random exponential 60. So that would be one thing we want to try. And then if we copy this down, so I do a Control C, come down here, hit Control V. Random exponential 60. And then over here, I want to do, I copied it again, random exponential 55. Okay, so what do we think is going to happen to our throughput? Yeah, I think maybe we might expect it to go down, and maybe just to make it a little bit more representative, maybe we ought to run it for more than just one day. Let's run it, run length. I'll specify to run it for a, what's going on here? Huh. Wow, I'm not quite sure what just happened here. Okay, we're not going to do that. I'm not quite sure what just happened. Oh, there it is now. So if instead of running it for that, let's say we run it for 5 days. So there's my run length of 5 days. Still do 10 replications, and I'm going to reset the first one and run it again. Okay, so in our first one, we ran for 5 days, so we had 120 throughput, and that's what we'd expected. For our second one, we used the random exponential on the inner arrival time, and we lost 6. On the next one, we ran random exponential on both of them, and we lost another 1. Now, in fact, the longer you run this, the more dramatic the results become. So if we, not for longer replications, but for longer time intervals, the longer you run it, the more dramatic it is. Okay. Okay. This shows a little bit more running for longer periods of time and shows that how the utilization stays pretty much the same because our averages are the same. But looking at waiting time, which is what we were looking at originally, the waiting time goes way up in these two distributions. So throughput doesn't get affected a huge amount, it's some. Utilization gets affected hardly at all, but the waiting time goes way up. So I guess the moral of this story is to search for and eliminate sources of variation in the system. So that's principle one. And at this point, since I don't have anything in particular that I feel the need to get through in this module, if anybody has any questions, I'll pause every now and then. And if you have any questions, feel free to ask questions about what I'm talking about, or anything else is fine. Okay, without any questions, you got to be quick. Without any questions, by the way, if anybody wants to type into the chat window, I won't see it, but you can bring it to my attention and we'll stop and take it there too.
Sounds good, yes.
Yeah, by the way, I haven't figured out how to show your chat window yet. Okay.
So yeah, if anybody has questions, please type them away in the chat box and I'll make sure they get addressed today. Thank you. Yeah. All right, go ahead, Dave.
Okay, so principle 2 in the PIP book is higher utilization increases work in process and waiting time. So what we want to do here is explore the effect of high utilization, predicting utilization for validation purposes, and look at some experimentation. So I guess the first thing is, what is verification and validation? So I briefly mentioned these before. Verification is basically, does the model work as you think it does? Did I make any implementation errors? You know, I meant to add 3 plus 5, but I actually added 3 plus 4, or I subtracted 3 from 5, or something like that. That's the purpose of verification, is to say, did I implement it correctly as I intended to implement it? Validation is more comparing to the real system. Does my model behave enough like the real system to draw meaningful conclusions? And again, we're not looking for dead accurate. The only dead accurate model is the real system. But you know, does it behave enough? And this is one thing I haven't talked about near enough, the validation and verification. And by the way, there's a somewhat subtle difference between the two, but it's important to just remember both concepts there. The best technique that I can recommend for making sure that a model is valid is each time you do an iteration, before you press the run, think through what your expectations are. You know, if I'm going to make a run and I expect my utilization to be 65%. Okay, and I make the run and it comes out at 50%. Well, does that mean I'm wrong? Not necessarily. It means, you know, one of several things. Either I'm really bad at estimating, which is okay, or perhaps I made some false assumptions, and so, you know, or I don't really understand the system well enough. So, you know, I was wrong at assuming it should have been 65%. Or the reverse is, maybe it should have been 65% and I implemented something wrong in the model to make it 50%. You know, I'm not trying to get dead accurate in these estimates. All I'm trying to do is get a ballpark estimate before you hit the run button. And the reason for that is human nature says, when I get a number, I want to assume that the number is right. So if I don't make that estimate and I just run it and I get a utilization of 50%, I'm going to say, oh, that's 50%. Yeah, that must be right. Where if I've upfront made an estimate and I estimate at 65%, now I have something to compare and question myself on. And it can tell me a good idea. So it's always good to do such expectations. And it doesn't have to be utilization. It can be anything, but just create some expectations. Like in the last model we did, when I had fixed things happening, maybe my expectation would have been, how many entities do I expect to get through that? And I said that they came in 1 per hour and none of them ever had to wait. Therefore, I could expect in 24-hour period to get 24. So that's my expectation. If it came back and I only got 16 through, then I'd say, hey, what's wrong? Was my expectation wrong, or is the model wrong? And that question can often lead you to a much more valid model. Okay, so we're going to set up a model with an inner arrival time of random exponential 0.25 and process and scenarios with processing time of 0.14, 0.20, 0.22, and 0.24. What are the expected utilizations for each of those? Now, I guess the first question is, how do we determine expected utilization? Well, expected utilization is basically the processing time divided by the inner arrival time. So if I have an entity come into the system every 0.25 minutes, and it takes exactly 0.25 minutes to process, it'd be 100%. If I had a processing time of 0.2 with my inner arrival time of 0.25, then it's 0.2 over 0.25 is an 80% expected utilization. Now, again, we're not looking for anything that's dead accurate. All we're looking for is a ballpark figure to help us, assess the validity of our model. And so we can, we're going to run an experiment, and based on that experiment, these are the expected utilizations I'd like to get out of that. Okay. So let's go back to our model. In this case, let's see. So we've got our inner arrival time and our server time. So we've actually got it all set up to do a totally different experiment than we were doing before. So in this case, let's say our inner arrival time, and we could use either fixed numbers or exponential. Let's use the exponential. So since I obviously don't type very well, I'm going to copy and paste this. So my random exponential, and actually we said our inner arrival time is always going to be 0.25. So let's copy that. Okay, so there's my inner arrival time control variable. And then my processing time, let's keep that random exponential. But let's make it, again, the 0.14, 0.20. 0.20. 0.22. And 0.24. And let's see. Reset. Let's reset this back to 1 day. Okay, so let's run it and see what kind of results we get. Oh, we're looking at throughput instead of expected utilization. Let me go back and cancel that and add a response for expected utilization. And my utilization, anybody think ahead of me what the utilization needs to be? What object are we trying to look at?
The server.
I'm trying to look at the server. And where do I find utilization on the server?
It's capacity, is it?
Yes, capacity dot scheduled utilization. Okay, so let's reset and run this again. And the numbers that we had predicted were 56, 80, 88, and 96. 56, 80, 88, and 96. So those are all within the statistical. Again, if we look over to our pivot grid, it will tell us what the results of each of those would be. So here, let's see. Server 1 scheduled utilization is 56%, plus or minus 0.6. So that is within the statistical range. By the way, I didn't show you this before. When you run multiple scenarios, the multiple scenarios show up in the pivot table as extra sets of columns here. So there's my 4 scenarios. Okay, so basically this confirmed what we were looking at. And you can see from the chart here that as the utilization gets higher, the effect on WIP gets tremendously higher. So even at 96% utilization. So a lot of people, a lot of managers look at utilization as, gee, I want my utilization to be as close to 100% as possible. And certainly from a standpoint of effectively using the resources, that's a good thing. Well, potentially, particularly if it's a machine, not a person. But when you talk about system, the impact on the system overall, once you get up above about 80 or 85% utilization, your effect on WIP becomes extremely high. And so you need to take that into account. Don't just automatically drive towards highly utilized resources if WIP is an issue. Okay, principle 3, constant WIP or con-WIP strategy has less WIP for the same throughput. Now, okay. So there's a couple things here. So less WIP for the same throughput. Does that make sense or not? Is that intuitive? That if you say you have a constant WIP, you can get by with less WIP as opposed to letting the WIP vary. So let's look at a couple things here. So we want to first place our source 3 servers in a sync, connect it up with 3 paths and set the inner arrival time to random exponential 4 seconds. So this gives us a chance to actually explore some new features in Simio. So I'm going to do file new here again. Okay, so we're going to put in a source, double click on the servers, put in 3 servers, and a sink. Actually, I'm going to move these closer together so that I don't have to, well, draw all the paths. Or do I? Maybe I do. Okay, so I'm going to put some paths in here. Okay. Yeah, I'm that kind of guy. I need straight lines. So we want to make our source be random exponential 4 seconds. Okay. Okay, if we just run this, what do we think is going to happen? And again, this is part of our validation. Always before you press the run button, have some expectations of what's going to happen. Okay, so I'm going to create a bunch of entities here, and they're going to get processed somewhere over here. Where are they going to go? Well, what I haven't shared with you yet is by default, if you don't specify anything else, entities will go by something called selection weight, which basically every link has a selection weight. And so the selection weight on each one is 1 by default. And so what it's going to do is say, well, the total of these 3 is 3. And so 1 out of 3 times it's going to go this way, 1 out of 3 times it'll go this way, 1 out of 3 times it'll go this way. But it is random, not cyclical. So, and it doesn't always look random when you get 4 or 5 in a row go to the same one, but it is random, so they're all going, spread out. So, automatic behavior is nice. It's nice for building quick models. It's nice. It's a good prototyping feature. But in terms of real models, it's pretty infrequent that you would want to do that type of thing. So what else can we do? Well, in here, if we want, in our outbound link, we can decide where we want it to go next. And so if I say I wanted to, where do I want this entity to go? My choices are, well, if the entity had a sequence, basically a process plan, then you could say, well, go wherever your sequence says to go next. If your sequence says process at the drill and then the mill and then the lathe, then that's what you're going to do. Continue says, I'm just wherever I was already headed, I'm going to continue going there. None says, nope, I'm not going to go anywhere. I'm just going to destroy the entity. So those those 2 aren't all that useful. Select from list or specific are pretty useful. So if I say specific destination, then it asks me, where do I want to go? So I might say, well, always go to server 2. So if I run that now, every entity is going to go to server 2, and now server 2 is getting backed up because it can't handle all that workload. Okay, so that's one option. Or I might want to say, select from a list. A list of what? Well, a list of servers or a list of nodes. How can I make that list? Well, there's a couple different ways. I could go over into definitions lists and create a list of nodes here. Or the easier way in many cases is to just use that multi-select. So I click on the first node, the second node, the third node, right click and say add to node list, create a new node list. My node list is named servers. So now I can go back here and say, well, go to my node list of servers. Oh, by the way, I guess I didn't point this out because it's so common nature to me, is that whenever you have a required operand or any error that's put in, but in this case, the error was the fact that I selected something that required more information and I didn't provide that information. Well, that automatically shows up in an error list at the bottom. So even when I am in other places, I can double click on this and takes me back to the error in the list. And in that error, then I want to say, oh, we'll put in the node list name of servers, and now I've got a model. So now that I have that node list names of server, I can say, well, select from that list, but select it in some preferred order. So what kind of options do I have? Smallest distance, largest distance, preferred order, cyclic. So let's try cyclic as an example. Cyclic will generate similar results that we had before, except that it's first, second, third, fourth, fifth, sixth, seventh, eighth, ninth. So it's a perfectly balanced set. So that's cyclic. Not real useful, but sometimes useful. Random would be exactly what we did to start with. What is most commonly used is a smallest value or largest value first of some expression. Now, I will have to make a change here before this will make sense. Can anybody, so if we look at these and all of these have input buffers of infinity. So if I have an infinite sized input buffer and I put two entities in it, how much room is left?
Infinity.
Infinity, right. So our default rule doesn't work very well as long as you have infinite buffers. But as long as they are finite, it doesn't matter how big they are. As long as they're finite, then these work well. So I did a click, control click, control click. So I did a multi-select of all three, and I'm going to set this, well, let's just set it to 0 for now and see what happens. So if I set it to 0, and then I selected my goal of smallest value first of the default option, which is associated station overload. So basically that is a shortcut to say how many are on their way to that station, waiting at that station, or processing in that station. So that is what that refers to. And so it will go, evenly spread out the workload between them. And note when they're not available, when nothing is available, it will sit back here and wait for something to become available. Now, when these are all the same, it doesn't show up that well. But let's say we set the time of this one to be 0.01. So much smaller than the other ones. Now we see that that third one gets a lot more throughput than the other two. Okay, so what we just talked about really quickly was link weight. We didn't talk about shortest path, but I'll just say that Simio will automatically find the shortest path through a network, no matter how complex it is. It will automatically find the shortest path through it, and even allows you the option of like disabling paths or reversing paths or changing a path between bidirectional and unidirectional. And anytime you make any of those changes, the shortest paths matrix is updated, and so we'll always continue to take the shortest path. Okay, so we've done some work. We tried a little bit with selection weights. We tried a little bit with creating a list for a node list. We explored a little bit of routing behavior with cyclic and random in setting our selection goal to smallest value of something. And there's a lot more things you can do. And I hope you recognize I'm only just barely touching the surface of some of these things that we can do. Let's see. So we wanted to convert this to a conwip system. Let's see, I don't know if my model is too far gone to get this or not, but yeah, let's stop this. We want to set this back to what it was before. So I think that is now back to what it was before. And a conwip system. So I think we wanted a conwip system with initial number of entities set to 6. So how do we do that? Again, we come back into our inner arrival mode. And we say we want this to be on event with 6 initial entities, and we want to create a new entity whenever anything leaves. So input at sync 1. So whenever anything goes into this node, we want to create another entity over here. So that's our conwip system. Let's see if it works. So there's our 6 entities. Oops. So I know there was a principle in here we were trying to get at, but actually I was more looking at it just to teach you a little bit about the node routing. So any questions on the node routing before we go on to another principle? I know I covered that super quick.
Do we have any questions, folks? I don't have any either.
Okay. All right. So what we want to do here, the next principle is basically compare parallel servers to multi-capacity server. So I think it's probably best if I just start over again. So we create a source, 3 servers, and a sink. And we create another source and a single server and a sink. And for these, we connect all of these 3 together. Okay, so we have 2 parallel models here. We're going to set this again at 4.5 seconds. And we're going to do the same here. Set this at random exponential 4.5 seconds. And here we're coming in and going to one of three servers. Here we're going to come in and say I have a fixed capacity of 3 servers, which means this one server can do 3 parts at a time. So what do we think is the difference between these? Which will perform better, or will they both perform the same?
Parallel servers will perform better.
I'm sorry, think which? The bottom or the top? Which one will?
The top.
Top will perform better? Actually, in order to tell this, I think we need to have some different model entities. So we have our default entity and our model entity 1. And let's call this red part and blue part. And I guess if we're going to call them red and blue, we ought to make it red and blue. So there's my red parts and blue parts, and source 2 is going to create blue parts, and source 1 is going to create red parts. And so how do we tell which one is working better? I guess we could look at time and system of source 1 versus source 2. Would that make sense?
Yes.
Okay. So let's run it again, make sure it's working. Okay, so it seems to be working. Fast forward. Now, I said earlier on, never make conclusions based on one replication, but we're going to look at one replication anyway. And look at the blue parts. Look at time and system is 0.099 hours. Here, let's change this. I told you we could do it, but I didn't show you how. So let's change it to minutes. There. So my blue part time and system is 0.59 minutes, and my red part time and system is 1.08 minutes. So the red parts actually took almost twice as much time in system as the blue parts. And this actually tells you why. The ending state tells you exactly why. In this case, there was only one queue. And so whenever any one of the 3 units became available, it would always use what's in the queue. In this case, we had 3 different queues set up. And so it was waiting in any of those 3 queues. And in this case, it just so happened that through randomness, it was assigned to queue number 3 when server 1 was idle. And so even though there's something going there, what about all these guys that are waiting? So in general, you can decrease the WIP by having only a single queue or a single waiting area. And that could be as well as putting it back here. So I think we would see that they had similar results if we did the select from list as we did before. So let's try that and see. So click, control click, add to node list, create new node list. I'm just going to call it node list 1. Back here, we want to have our entity destination be select from list, node list 1, select available only. Let's see. I think that might be enough. Let's see if it works. No, it's not. So we also needed to, let's say that it has no space to wait. Okay, now let's see if it's working. Okay, so now it's forcing it to wait back here. So just by forcing it to wait back here and only go to normal, let's look and see. Our red parts now should be very similar to our blue parts. If we look in the results, red time and system 50 and blue time and system 0.57. Wait a minute, what's happening here? Minutes. I'm not sure what I just did. I'm sure I screwed something up, but I'm not quite sure what I just did, but I'm sure it's my error. Okay. Okay. Actually, I think we are out of time. Actually, I just went over time, didn't I? So that's probably a pretty good place to stop. But I just want to illustrate, you know, there are more principles. I highlighted principle 8, 10, 13, 15, 16 are all interesting ones to explore. Transfer batching takes use of combiner and separator, but basically transfer batching says, let's say I had batches of 100 and I produce 100 and then send it on to the next machine and do the 100 there, and then send it to the next machine and do 100 there. Transfer batching says, well, maybe I ought to batch them up in 10 at a time. And so although my batch is 100, as soon as I process 10, I send those 10 on to the next process. And that can dramatically improve the behavior. Okay, so in summary of that, you know, I do encourage you to read the entire book. It's a quick read, and you might share it with you know, your favorite manager if you think that might benefit them. You can take the PDF that comes up here, and you can feel free to copy that and send it to other people if you'd like to do that. Okay, so I'll pause there again. If anybody has any questions, I'll take them now. Otherwise, we will rejoin in 10 minutes and go through some design and scheduling case studies for about 30 minutes.